Hello, everybody. This series of lectures is going to be about your gases and your gas laws, and how gases affect chemistry, and the way that we can use gas laws to interpret things about different types of reactions and special gas reactions. So, I'm just going to go ahead and get started here and go through these notes and kind of explain some things and hit some high points and some really important details of how gases really affect chemistry. You can go in terms of how gases affect your thermodynamics, how gases affect your kinetics, how gases affect even acids and bases. Again, so gases are really, really important. So the concepts aren't very difficult to grasp, but the material and the content behind them are really, really, really important. So just follow along with me as we go through this and take good, accurate notes, because it will definitely help you in the long run. All right, some of the things you need to know about gases is there are four quantities that you must be able to define, okay, whenever you're in a state of matter. Number one is the quantity of gas. Now remember, we always want to define a quantity if we're ever trying to compare it, definitely in moles. That's the first thing you need to realize is yes, you can have a mass of gas. Yeah, I get that. It can be in grams. However, if you're ever trying to compare different quantities, you're definitely going to need to get it in moles. This right here is a concept that if you have a highlighter or you like to star things or underline things, this right here is going to get you through some of the most important things in this gas chapter. And I cannot overstress the importance of that relationship. This relationship of 1 mole of a gas at STP is 22.4 liters. Now, there's two things that we need to define. Number one is we need to talk about this concept called STP. Now, I'm going to get to it a lot more in detail later, but if you want to go ahead and define it, what it stands for is standard temperature and pressure. Okay, that's what it stands for. Standard temperature and pressure. Well, what does that mean? What is standard temperature and pressure? All right. Well, the pressure, and again, this is something you really need to define, is 1 atm. Sorry, I'm kind of running out of room. And the standard temperature is going to be 0 degrees Celsius, which hopefully you know is 273 Kelvin. Now, what is odd about the temperature aspect of this? Because some of you may have looked at that and said, that's not right. That's not normal. That's not what we normally talk about. Yes, standard temperature is different than what we normally call standard conditions. Okay, there is a difference between STP, which is standard temperature and pressure, and then something that we call standard conditions. I want you to think of this in two different aspects, in two different ways. If I were to ask you or tell you that the room temperature currently in my room is 0 degrees Celsius, and I would ask you, would you need a jacket? Well, hopefully you know that 0 degrees Celsius is 32 degrees Fahrenheit. So the answer to that would definitely be yes. So you're going to need a jacket. However, standard conditions is a little bit different. The value for standard conditions is 25 degrees Celsius, or 298 K. Again, I'm sorry, I'm kind of cramming all this in. There's a difference there, and it is hard to remember. And this is one of the aggravating things about chemistry. Sometimes is that you kind of run into what I call conditions. Remember how we have the not symbol, and again, that's just standard. And then we have STP. So the major difference is the fact that we have a temperature difference. Okay, I'm sorry, I'm just going to go ahead and do this, make it a little bit easier. Your T, its standard conditions, is 25 degrees C and 298 K. At STP, your temperature is 0 degrees C and 273 K. Now, I know what you're thinking. Well, we already know that this is 32 degrees Fahrenheit, which is extremely cold. So what is that in Fahrenheit in terms of 25 degrees? Well, you're looking at about 77 degrees Fahrenheit. So no, you would not need a coat. And if most of the time your room temperature of stuff is going to be between 73 and 77 degrees, depending on what's going on around you. And this is the thing that most reactions are ran at. They're ran at most of the time they ran at temperature, room temperature is what I'm trying to get to say. But there is this factor called STP that we need to be aware of, okay? The one last little factor that I do encourage you to know is that your pressure of standard conditions is also 1 atm. So the pressure doesn't change. So the only difference is your temperature. And again, I wish there was an easy way to remember it, but I don't have one. All right, so that's number one. Number two, the temperature. This is the biggie as well. You need to also make sure that you know that every time we do a temperature, it must always, always, always be in Kelvin. The volume must always be in liters, and the pressure must always be in atmospheres. And I know what you're sitting there thinking. All right, I see that we have an N value. I see we have a T. I see we have a V, and I see we have a P. Well, I really, really hope that by that point that, let me clear all of this, that if you see all of those things, that this law right here is probably going to come in effect somewhere down the line. And you are correct in assuming that. The only value that you do not know yet is R. We're going to talk about that in just a few minutes. And again, E, that almighty and all important 1 mole of gas, 1 mole of gas is 22.4 liters at STP. Now, the other thing that I want you to think about whenever we're talking about this is how much room that takes up. If I were to ask you to go to the store and buy a 3-liter Coke, you know what a 3-liter Coke looks like. That's a rather large capacity. Think about 22.4 liters. That's a lot. Okay, I mean, it really is. It boils down to be several Cokes if you want to think about it like that. In reality, you're looking at almost 7.5 3-liter Cokes. That's about what you're looking at. So again, just kind of keep that in the back of your mind as we go through this. One of the other things is this very bottom statement. Is a gas uniformly, now what does it mean by uniformly? Let me go back. Sorry. A gas uniformly means it goes in the same direction at all the same time, fills a container, is easily compressed. All right, well, you all know that if you take a water bottle that's empty and you start squeezing it around and it's going to build up pressure. And then also mixes completely with any other gases. So gases do have those abilities. So it can fill a container, it can be compressed, and it can also mix. All right. Now, where does the gas pressure actually come from? Well, this is the basic definition. A measure of the force that a gas exerts on the container. Now, think about that. We need to talk about the way we get pressure is because of force. Well, where does the force come from? Well, let's read the next statement. Force is the physical quantity. Now, when it says a physical quantity, that means we can put a number to it. We can measure it. That interferes with inertia. Now, what is inertia? Basically, that means that any object in motion will stay in motion unless enacted upon by an outside force. Well, guess what that outside force is? You bet it. Gravity. Gravity is the thing that's going to stop an object in motion. Okay. Some other factors are going to be friction and things like that. So force is basically anything that has a physical quantity that interferes with inertia. And then it goes on the very last statement. It says gravity is the force responsible for weight. Now, the little concept that I kind of want to talk about is that if we have Sally, all right. Again, this is Sally. Give her some here. And we put her on the scale. And let's just say that she weighs 100 pounds here on Earth. Okay? That's what the scale says, 100 pounds. I think some of you are probably thinking, wow, I wish I could weigh that much. And then we take Sally and we send her to the moon. All right? Well, the problem is that we know that the gravity is less on the moon by far. So we've got to figure out what her difference would be. So let's just say on the moon, she goes up there and she is 44 pounds. Now, what causes her difference in weight? Because the question remains, is Sally still Sally? Yes, Sally is still Sally, so she doesn't change who she is. So her mass is equal, but her weight changes. And so that's kind of what this statement was telling you, is that gravity is the force responsible for weight. So no, if you change your source of gravity, then you will change your weight. Okay, now this part of down here, this bang, 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 what I was referring to is basically how do you get gas pressure? It's these gas molecules that hit the container that they're in that will cause the gas pressure. All right, force and pressure. Now, these are two things that you really need to kind of come up with. This is more of a physics concept. However, it does have an application in chemistry as well. Force and pressure. Force is equal to mass times acceleration. Well, if you really want to if you like formulas, if you're like some people, and you like formulas, then the formula for this would be F equals ma. That's your formula. So F equals ma. That's your formula. If any of you taken physical science or you've taken a physics class, then this will definitely um, be familiar to you. Also, this is Newton's second law if you want to go back and look at that. But here's the cool part. Acceleration is caused by gravity, and this is some of the concepts that a lot of students have a hard time understanding. That if I throw up a ping pong ball and I throw up a baseball, if I throw them, or let's do that. Let's say we drop them. If we drop them from the exact same height, they will hit the ground at the exact same moment. The reason why is because the force that is applied to those two objects is the exact same. Because gravity has a constant force on an object, no matter the mass. They will both travel at 9.8 meters per second. So acceleration here on Earth is a constant. Again, one more time, acceleration is a constant. So if you're trying to figure out how much force an object has when it hits the ground, this is the formula you plug it into. Now, of course, if I take a ping pong ball and I drop a baseball, their force is definitely going to be different. However, the speed or the velocity at which they drop will be the same. They'll hit at the same time, but why will their force be different? Well, if it's a constant, if you plug in 9.8 and then you multiply it times their mass, well, which object has a higher mass? Well, obviously a baseball does. So baseball's mass will be higher. So mathematically, a higher number times a constant will give you a higher number in the force. All right, so just kind of keep that in mind. The units of force, the SI units, if you will, are going to be newtons. All right, so this is your SI unit. This is the one that you're going to see most often. However, we can take that unit and actually break it down a little bit. So think about it. What is the SI unit for mass? Well, the SI unit for mass is the kilogram. Now I know what you're thinking. Wait a minute. Why is it not the gram? Remember, the gram is so small that most things weigh at least 1,000 grams. So the base unit of mass is going to be kilogram. Something you may kind of want to keep in mind, something that is about 1 gram is a paperclip. Well, obviously, a lot of things weigh more than a paperclip do, so that's why we use kilograms. All right, well, notice what it is, the mass of kilogram, and notice what acceleration is. Again, we said it's a constant, so your unit for acceleration is meters per second. All right, well, look at what we said. We said the unit is newtons, so how do we get newtons? So if force is a newton, then the way we got it was kilograms times meters per second squared. Matter of fact, there is a small typo. Please excuse me. It is actually meters per second squared. I did leave that off. I do apologize. All right, so again, that is force. Now, force can cause pressure. Well, notice what it says. Pressure is the force applied per unit area. And the best way I have of an example of this is think about a ballerina. All right, imagine a ballerina is standing flat-footed. Think about the amount of force that her body is applying to the floor beneath her. Well, the force that she'll be applying is basically her mass. Whatever her mass has applying to the area beneath her. All right, now imagine that same dancer then standing on one leg. All right, so what we have essentially done is we have now taken two legs over a larger area, and now what we have done is we have focused it in a smaller area. So now we are focusing all of our mass in one area. Well, then imagine if we take that same foot, again, let's just kind of make this the foot, and then we go up on one toe. Well, then what have we done? We have even centralized more of the area to the very point of the toe. So if we were able to take the pressure underneath her foot whenever it's flat, and then underneath when she is just on one toe, I can guarantee you that the amount of pressure under one toe would be much greater than just under her foot. So the amount of area has a large deal with how much pressure that you can be applied. So again, it's force per unit area. Well, what kind of unit do we have there? Well, we have just determined that force is Newton. Well, area, remember, if we have the area of a square, it's length times width, so it's only going to be 2 dimensions. So it's Newton divided by meters squared, because we only have 2 dimensions. All right? So again, that is going to be your pressure. Now, we're going to get into something else in just a second. So how do we measure pressure in terms of gases? The first measuring of atmospheric pressure was developed by Evangelista Torricelli, and again, 1643, long time ago. And what he developed, and again, a lot of you have heard this. If you love the Weather Channel, you've definitely heard this. It's called the barometer, not the barometer. It's called the barometer. And if you break this word down, which I really like to do, baro means weight, and meter means the measure. So basically, we're trying to measure how much weight we have pressing down on something. And I have a little description of here of how he did it. I'm just going to kind of use the picture to describe it. What we have is we have this dish, and in this dish we have the element Hg. Now think for a second, what is Hg? Hopefully you said mercury. And inside this dish we have this long cylindrical column that has the ability to absorb the liquid. All right. And what happened is whenever Torricelli put this together, he noticed that there was a pressure being forced down on this liquid. And whenever the pressure was pushing down, he noticed something. That the liquid in the container went up into the tube. And so he was thinking, all right, how can I connect these topics? How can I figure out how much pressure, how much atmospheric pressure was pushing down on this liquid? Well, what he then did is he took a distance from the top of the source of the liquid all the way to how far it went up. Now, you can barely see it, but right here it says it. And again, I'll write it out the side if you can't see it. What he got was 760 millimeters. That's how high the column of liquid went up into the tube. And so he correlated that. He said, okay, well, he said, let's call that a constant. Let's call that a variable relationship. So what he essentially said was that if you have 1 atmosphere of pressure pushing down on a liquid, the distance that it traveled up was the variable relationship. And so what he was able to determine is that 1 ATM, and again, I'm going to explain this a little bit better once I use the formulas here, that 1 ATM, again, which is the pressure that is constantly pushing down on us, made the column of mercury rise 760 millimeters. Interesting. So that is our relationship that we really need to keep in mind. There is another thing that I do need you to understand, and again, the 760 millimeters is, again, the distance that the column of mercury rose. Now, again, what was the guy's name? It was Torricelli. So they actually did give him a little bit of credit, and they said 1 millimeter of mercury is equal to 1 torr. So that is one of the hard things about pressures, is that there's so many different units to deal with that you just kind of have to figure out and know some of the conversion factors. So we do know that 1 millimeter of Hg is equal to 1 torr. So 760 millimeters of mercury is equal to 1 torr, but it's also equal to 1 ATM. Okay, that's the biggest conversion factor that you must memorize. And here's the even bigger one. I'm just going to kind of start down here. But see, atmospheres is not the SI unit, which you would hope and you would think that it would be, but it's actually not. It's actually called the Pascal. The guy named Blaise Pascal was who they named it after. We're not going to really get into him. But what a Pascal is remember, this is the amount of pressure per area. Because remember what I said. It's the amount of pressure that's pushing down over a certain area. All right, well, let's think. We know that force is a Newton. All right, well, we know that, it's the amount of force that's pushing down. So we know that force is a Newton. We know that area is meters squared. And so we have this other concept of a Pascal. So there's newtons, there's pascals, there's millimeters of mercury, there's atmospheres, and there's even another one. If you ever watch the Weather Channel during hurricane season, they talk about bars and millibars. Again, and so there's several different units of pressure. But let's just be honest with each other. The ones you're mainly going to see are atmospheres and pascals. Okay, and just I really wish I had an answer for you. I haven't seen it done a whole lot. I've never seen a conversion factor, but if you ever do have to convert between atmospheres and pascals, now there's something funny here. Notice this is kPa. So what that really is that's 1,000 pascals. So 1 atm is equal to 101,325 regular pascals. Okay, so make sure you kind of keep in mind. So this Kp is kilopascals. All right, again, and I'm just kind of re-explaining this whole concept of where did the 760 millimeters of mercury come from. The normal pressure due to the atmosphere, and here's the key part that I did leave out. This was all at sea level. All right, again, the column of mercury will go up 760 millimeters. So that was one pressure. So let's talk about that for a second. So let's go back to this and let's clear. All right, so let's pretend for just a second. Let's see if I can do a good drawing here. All right, and let's just pretend that we have the ocean. Ooh, that's not what I want. Hold on, my apologies. Thank you. All right. So let's just pretend for a second that we have an ocean right here. So the point at which you have 1 atm is only going to be at sea level. All right, so this is at sea level. So anytime you are measuring your millimeters of mercury, it will be 760 millimeters at that point. Well, we need to know something. As we rise in altitude, now remember, altitude just means going up in the air. What happens to your pressure? As you go up, your pressure will decrease. So what does that mean? If I go up here to the mountain, and I went to almost the top of the mountain, and I try to measure what my millimeters of mercury would be, since the pressure pushing down on that liquid will be less, then my number value will be less than 760. That'd be less than 760. Well, let's all of a sudden say we go down here to the bottom and we're in a submarine in the bottom of the ocean. Okay? Well, I should also know that the further I go below land, that means my pressure should increase. Okay? Well, if my pressure increases, that means my millimeters of mercury that I just measured will be higher than 760. All right? So again, depending upon where you are measuring these things, depends upon the amount of pressure in your millimeters of mercury. But as a standard, we say everything is 1 atm and 760 millimeters of mercury. Okay? All right, so let's talk about a little bit more about pressure. Pressure is caused by collisions of molecules. Guys, this is probably one of most of the important slides that's in this packet of notes to begin with to understand basic concepts. So I would put a big circle around this slide. Okay? It is caused by the collisions of molecules. And this is kind of how I want to teach the concept. Well, imagine if we were out at break, but I only let the seniors out for break today. Well, that means my number of molecules, and let's say every person is a molecule, is way down. Well, the less molecules you have, the less people you have bumping into you. All right, well, the next day I let juniors and seniors out. Well, that means I'm going to have more molecules. That means the collisions are going to go up. All right, well, let's say the third day I'll let everybody out. Freshmen, juniors, seniors, and sophomores. Everybody's out in the commons area where we have break. Well, that's going to be a huge problem because that means we have a ton of molecules. That means we're going to have a ton of collisions, which guess what? That means our pressure is going to go way up. There's more of a chance for people getting an argument, people getting mad, people getting frustrated. So the pressure of the overall container is definitely going to increase. So that's number one. So we have more collisions, we have more pressure. All right. Well, just like I just said, well, what if you add more molecules to that concept? Well, the more molecules we have, the more collisions we have, the more pressure we get. Well, that's a common sense approach. All right, the next one. You should definitely know this. Higher temperatures, and I have said this a million times. You heat them up, you speed them up. Well, the higher the temperature, the more the velocity the particles have, the more violent collisions you have. So let's take break. Instead of everybody standing around and hanging out, everybody has to run as fast as they can possibly run around the break area. We all know that that is going to turn into just pure chaos. And so you're definitely going to have a lot more violent collisions. Well, the more violent collisions you have, the more pressure you have, and that. All right, so that's the second concept. So the first one, more collisions, more pressure. The more molecules, the more collisions, the more pressure. The higher the temperature, the more the velocity, the more violent the collisions, which equals more pressure. And then finally, the last topic, or the last little way we could talk about, is what if we take the container and make it smaller? So instead of break being in a huge area that we have it, what if we had break in one classroom? It'd be ridiculous. It'd be crazy. Or if we had to go just to the lunchroom. So the container also has a lot to do with it, okay? So the smaller the container, the more collisions you have, the more pressure you're going to have. So this is a very important slide for you to understand. All right. This is something that I don't really want to waste a whole lot of time on. This was another way to measure pressure. It's called a manometer. And this is what I want you to notice. The top two things right here, this is where your pressure will begin. All right, the top two things, the pressure is pushing down this tube. Well, if you notice something, the tube on the left, the distance is much, 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 much greater. So what's happened is essentially, imagine taking a straw and you blowing the liquid down because there's a lot more pressure. Well, what's happening here is the flow of the liquid starts and it's going to move this way. Well, the harder you blow or the more pressure there is, the further that liquid is going to end up moving around that tube till eventually it comes over here. So this is A. Well, that means there's a lot of pressure in this tube right here because it's forcing it down. Well, if you look at B, notice where the liquid height is. There's not a whole lot of liquid height at all right there. So essentially what we've done, there's two ways to look at it. If you go from A to B, the pressure has been relieved. And as soon as you relieve that pressure, if you basically essentially eliminate that, the liquid is allowed to retreat back up to its original height, all right, which is what it means. So the pressure of the gas is given by H, and again, what is it talking about? H, basically it's this distance that it has traveled. The difference in mercury levels in units of torr, and again, remember, torr is named after Torricelli. He's the guy that invented this thing. So gas pressure equals atmosphere pressure minus H, and it's plus H. But again, this is just another way to look at it. Okay? All right, so here's what I want to talk about. The pressure of a gas is measured at 49 torr, represented in both atmospheres and pascals. All right, well, this is what we need to understand. We know that 49, excuse me, let me go back. Sorry, guys, this is the first time I've done it on this type of device. I'm learning as I go. All right, so we know that we have 49 torr. And just set it up just like a unit cancellation. And I'm going to go to atmospheres first. Well, if torr is on top, torr has to be on bottom. And then I can go to ATMs. But remember, what's your conversion factor? In 1 ATM, there are 760 torr, which will end up giving you a correct answer of, now there's two sig figs, let's keep that in mind. So 0.0064 atmospheres. All right, so that's the first one. And now I need to go to pascals. But remember, there was something very, very, very special about this one, okay? Let's just kind of start back over. So we have 49 torr. But there was not a direct correlation or connection between torr in millimeters of mercury and then pascals. So we're going to need to do something different. So we have 760 torr. And the first thing we're going to have to do is we're going to have to go into atmospheres first. Again, I'm setting these up different because imagine if you didn't have them. All right. And then 1 atmosphere, if you'll go back and look at your notes a few seconds ago, we said there was 101.325. Let's just say 33. Remember, this is the key part. It was kilopascals. All right. So again, kilopascals is a big deal here. So then we're going to have in 1 kilopascal, there are 1,000 pascals. All right, so that's kind of the way we can approach that. And then you can run your unit conversions there, and you should get 6.5 times 10 to the third pascals. Okay, so that's your answer. Now, on a better way to actually approach this and write this, I'm going to be honest, this is not a good way to write it. The way I would write it would probably be 6.5 kilopascals. That's a much better way to approach that problem. Okay, that way you eliminate the scientific notation. All right, rank the following pressures in decreasing order on magnitude. So basically, we want the largest pressure first. Apologies. We want the largest pressure first, and then we want the smallest last. But here's the issue here. We have a kilopascal, we have a torr, we have an ATM, and we have a millimeters of mercury. Well, the issue is that they're not all in the same unit. So we're going to have to get them all in the same unit. All right, so what I'm going to do is I know that that millimeters of mercury and torr are the same. I actually, for some reason, let me just go ahead and convert all these to atmospheres. It'll be a little bit easier to do it this way. If you convert the millimeters of mercury to atmospheres, you're going to divide that by 760, which actually ends up giving you 0.5 ATMs. Okay. If you do the kilopascals, you're actually going to end up with 0.75 ATMs. And if you do the 300 torr, you're going to actually end up with 0.4 ATMs. All right, so from that, now you can see which one's the largest. So you can do 75 kPa. Then you can do 0.6 ATMs. And again, I'm writing them in the units they were given in. You don't have to do that. You can rewrite them in the terms of what you converted them to. But remember, the best way to do this is make sure to convert them all to the same unit, and then you're going to be good. So then we have, the 350. Let me erase this. That's not going to erase for me. All right, so let's do 350 mmHg. And then last but not least, we have the 300 torr. Okay, so again, the key there is to just make sure that all of the only way you can compare them is to changing them to all of the same units. It does not matter which one you can change it to. And me personally, again, I have the answer key that I'm kind of going through and looking at it. I would change all of them to millimeters of mercury because these two are already comparable. And the reason why they're already comparable is because remember that 1 torr is equal to 1 mmHg. So off the top, you at least know that this one is higher than that one. So you can at least start from that aspect. All right. I'm going to be honest, I don't have the ability to do these. I'm currently recording at school and I can't pull up my YouTube videos. I may have some time a little bit later to show these in class just to kind of prove a point. But here's the deal. Most of these are going to be YouTube videos. And it's really interesting. So what I would encourage you to do is pause the video. If you're watching it at home, you're watching it on your phone, I do give you the actual title name of the video. Each one of these is a different video, and look them up. Really, really cool, interesting stuff. And I would have the ability to explain it. Could I show you the video? But again, that may be something I would have to do in class one day. Okay, but again, just pause the video, look those up if you would like. All right. Ideal gases, again, it's cut off at the top, but it does say ideal gases. Ideal gases are, and there is your key phrase right there, imaginary. What in the world is an imaginary gas? It's kind of like this concept that we would love to have this perfect student who does everything we ask, makes 100 on all the tests, turns in everything whenever we want them to turn it in. However, we know as teachers that that's probably not ever going to happen. We understand that. However, there is some things that we can do to try to make you perfect. We can try to make you as close to perfect as possible, which is what we call ideal. An ideal situation. My apologies, guys. Again, I don't mean to keep hitting that button. Okay, so again, ideal is kind of what we're trying to go for here. But what makes a gas ideal? Well, it fits perfectly all the assumptions of the kinetic molecular theory. Now, if you read some things, if you're looking in a book, if you're trying to look some stuff up, you may see the kinetic molecular theory shortened to KMT. Again, it's the exact same thing, kinetic molecular theory. There are 4 things mainly. There is a 5th one that I'm going to show you in just a second, but I do want you to understand that there are 4 major ones that you need to be aware of, okay? And again, this is version 1, so you're going to see version 2 in just a second. The first one, you definitely understand this, and I don't have any questions that you don't know what this is, because you've known this for forever if you've been in any kind of chemistry class. Gases consist of tiny particles that are far apart. That's the basics of any kind of gas problem that we would have. All right. Number 2, collisions between gas particles and collisions between gas particles and other particles. And then this is the other little concept you got to think. And the walls. It's not just between the gas and the gas. It's actually between the gas and the wall as well. Okay, really important. Are what we call elastic. That's your key word. If you're looking for a word to highlight, that's definitely the one I would be highlighting. The word is elastic. I want you to think about a rubber band. If you take a rubber band and you stretch it and you let it back go, what's going to happen? It's going to come back to its original size. Well, and it kind of works that way. Basically, what that means is if a gas molecule hits the wall of a container, that molecule is basically going to continue its energy motion, but it will be in the reverse direction. So basically the energy transfers from the molecule to the wall, and then the wall transfers every single piece of energy back into that molecule. So, and again, this kind of translates into number 3. No kinetic energy is lost in elastic collisions. So essentially, imagine this is kind of how I explain this. Imagine you're playing wall ball. Most of you know what wall ball is. You probably grew up playing it as a kid. Imagine throwing a ball at a wall, and when it hits, it comes back at the exact same velocity that you threw it. So it comes right back at you as hard as you threw the ball originally. We all know from years and years of experience that does not happen. The wall absorbed some of the energy. And again, this is why we call these gases ideal. We know they do not exist. Okay, so that's what you need to understand about this. Is we hope to get it this way, but we realize that it does not exist. All right, next. The volume of individual particles is 0. Now, we also know that is not true. If something is matter, it's got to take up space. Well, this just said the volume is 0. So this is why it's kind of one of those weird things that it's strange to get into. All right, now this is version 2 of your kinetic molecular theory. So you're going to see some very similar topics and ideas, but there is a few differences, okay? All particles are in constant, all particles are in constant random motion. Well, you know that's just the basics of chemistry. Everything is moving constantly because things are made up of electrons, and electrons are always moving. So all particles are always moving. And this is where it gets you. Until absolute 0. Now, what is absolute 0? In terms of its actual numerical value, it is 0 Kelvin. That means all motion ceases to exist. Well, we know, hopefully, or you know, that we have not hit absolute 0 yet. This is not something that is real on this planet yet. We've not got to it. So this doesn't exist. So since we don't have absolute 0, then the next statement must be true. They therefore possess kinetic energy, which is the energy of motion. We know that that is true. All right, so A was a little different. All right, part B. All collisions between particles are perfectly elastic, which means no energy is lost. Yep, we got that. We figured that out last time. C. The volume of a particle in a gas is negligible, which means it's approximately what? 0. We know that that's not true. We know that it does have to take up a little bit of volume. All right, we know A is different, and now we're going to get to D. D is also a little different as well, and this is very, very, very crucial. If I could point out one thing in this whole slide or this whole packet that's crucial to your understanding, it's this part right here, and you're going to see it 100 times between now and the end of this session. The average kinetic energy of the molecule is, one more time, the average kinetic energy of the molecule is, which means it is the same, is the Kelvin temperature. So the way we get our energy is by the temperature. One more time. The way we get our energy is by the temperature. So the only thing that changes is the temperature. So the average kinetic energy of the gas particle depends upon the temperature, not the identity of the particle. That is what students have such a hard time in understanding. If you throw them out, two different particles, and the question is which particle has more kinetic energy, as long as the molecules are at the same temperature, they possess the same amount of energy. That is one of the biggest trick questions in all of AP chemistry. They try to confuse you by giving you all these different particles, and they say, all right, which one of these particles has the most energy? They're trying to trick you. If they are all at the same temperature, they must possess the same amount of energy. Very, very, very crucial to your understanding. Please grasp that. One more time. The particle does not matter in terms of how much energy it possesses. The temperature is what determines it. So if any particle at the same temperature has the same amount of energy. All right, that's D. And E is also different as well. There are no forces of attraction between gas molecules. Please put this underneath this. Essentially what this is saying is that no IMFs occur. Well, how big of a lie is that? We know that that is one of the biggest lies you could possibly have, because everything has an IMF between it, no matter its structure or anything like that. And here's another way to kind of think of this in the real world. I realize that this is a large school, 1,200 students. You can't tell me that there is not one person in this entire school of 1,200 students that you don't think is attractive. I'm not saying you got to like them. I'm not saying you got to date them. I'm just saying that you think they are attractive. Again, because forces of attraction. You think they are at least attractive. That's the key. All right? Kinetic energy. Again, this is what we were just talking about. Remember that kinetic energy is equal to 1/2 mv squared. And this is a topic that I want to talk about. First of all, ignore that concept. It's just a matter of mathematical approach. All right? M. What is M? And I hope that you said mass, not molarity or anything crazy like that. And hopefully that you know that V is the volume. Excuse me. Wow, I just did it. That's what everybody else says. It is not volume. It is velocity. My apologies. All right, so the kinetic energy is dependent upon these two variables, the mass and the velocity. Well, let's talk about their relationship for just a second. All right, so we know that Ke is equal to 1/2 mv squared, where m is mass and v is velocity. Well, let's take that ping pong ball, and then let's take that baseball. And we were to put these on a scale. And let's just say for fun that your baseball is 3 pounds. And again, I'm making things up. And your ping pong ball is 1/2 pound. We could agree that this is a decent approximation. So based on this formula, so far, our M value, our mass value, is much greater for our baseball. So what you're going to want to think is, oh, well, if that's the case, then the baseball will have higher energy. That is wrong, and remember, I told you this just a few moments ago. No matter the object, baseball or ping pong ball, as long as they're at the same temperature, they will have the same kinetic energy. So what we're telling you here is that your kinetic energy between these two things is ideally and theoretically equivalent. They're equal, your kinetic energy. Well, I know what you're thinking. How in the world, if a baseball is 3 pounds, and again, guesstimating, and a ping pong ball is 1/2 pound, again, guesstimating, have the same amount of energy? It's a fact. Here's why. Because if you take these two objects, and again, you've got to think we're talking about gas molecules, not baseballs and ping pong balls, okay? if I were to put these two in a race, who's going to win? Well, I hope at that point you hopefully said the ping pong ball is going to win. Why would the ping pong ball win a race? Well, if you said the fact that he is lighter, then you are definitely correct. Well, if that's the case, then that means its V value, its velocity, is going to be greater. So here's the relationship that I'm trying to get you to understand. As the mass increases, the velocity must decrease. So these two factors are interchangeable in terms that their ratios allow the constant, the kinetic energy, to be equivalent. Again, at the same temperature for any molecules, it will be the exact same amount of energy. One more time. These two variables, the mass and the velocity, offset each other so that as your mass increases, your velocity must decrease, and vice versa. If your mass decreases, which means it gets less weight, then your velocity must increase. And they offset each other, which means that as long as you are at the same temperature, any two objects will have the same energy. That's the key to this. All right. So also the temperature is the measure of the kinetic energy. So the temperature and kinetic energy are what, class? Directly related, which means as your temperature increases, then what does that mean? Your kinetic energy also does. Well, hopefully you said your kinetic energy also increases with that. Okay. All right, we got a few more slides. Let's do 3 more slides, and we'll cut this video off. All right, the nature of gases, and this is something that I've kind of mentioned just already a few times. Gases expand to, again, fill their containers. Basically, they just don't leave half the container empty. So imagine if you had a, if you have a Diet Coke bottle or whatever you want. Again, I'm not the best drawer. Basically, it's not going to draw a line right here, and all the gas molecules are going to stay below this line. No, if it is sealed here at the top, the gas molecules are going to go everywhere. Of course, they won't go outside the container. That doesn't make sense. But again, they're going to fill their container of whatever they're in. Okay. The next one is gases are compressible, which means you can put them into a small area. But here's another thing. I want you to understand this. If you compress them, the pressure must increase. All right. If you compress them, the pressure must increase. Gases are fluid, which means they can flow. They have a low density. It's 1/1000th the density of equivalent of a liquid or solid. Again, it's they're very spaced out. And there's 2 other topics. We're going to get to this way later in these notes. But gases effuse and gases also diffuse. Now, what does effuse mean? Basically, the definition of effuse is when a gas will pass through a very tiny opening. Well, think about this. If you're spraying cologne or perfume, as soon as it exits that little bitty hole, that's what your effusion is. Now, diffusion is, imagine if I'm standing in front of the class and I spray something, and it takes a few seconds, in the back of the classroom you can finally smell it. Well, what that tells me is that gas was able to mix with all the other gases and to spread out and mix. So again, to diffuse means to spread out and mix. So basically, smelling perfume across the room is a good definition of diffusion. All right? Now, we've already talked about this, and this is something that you really need to grasp, you need to understand, okay? That what is STP, and it's hard to get. I understand that. And there's no way to get around it. You're just going to have to put some time and effort in. This is the kicker right here. STP, standard temperature and pressure, has a temperature of 0 Celsius or 273 Kelvin. Now, the fact is, the reason I keep throwing in this 0 Celsius is because you understand how cold that is. You know that that's 32 degrees Fahrenheit. You know that that's freezing. But we also know that anytime we do a calculation or conversion, we must always be in Kelvin. So that's really the number you need to memorize, okay? Right. The molar volume of a gas, again, at STP, it takes up 22.4 liters. So that's probably the 3rd or 4th time you've seen it. And again, one more time, 1 mole is 22.4 liters at STP. Now, I'm going to tell you in the problem, how will you know it's at STP? You will see this right there. That's how they'll label it, okay? And again, just memorize that. It's a fact that you're going to need to know. All right, last slide, and the only reason I left this in here is because somebody may have forgotten what it is, but hopefully by this point you do know what it is, and you shouldn't need any help in terms of remembering what it is. Okay, so again, converting from Celsius to Kelvin. If you need Kelvin, you got Celsius, add 273. If you need Celsius and you have Kelvin, just subtract 273. All right, that is the end of this recording, and hopefully you have gotten a lot out of it. I appreciate you watching.